Okay, I think we can go ahead and get started at this point. So it's a pleasure today to welcome our lunch speaker, Emily Cunningham. Emily is a Flatiron Research Fellow at the Center for Computational Astrophysics. I just learned that 6 months from now in September, she'll be moving to Columbia University as a Hubble Fellow. So Emily's work focuses on understanding the Milky Way stellar halo, using the motions and chemical properties of stars to understand the formation and evolution and structure of the Milky Way halo. And that's what she's going to tell us about today. So take it away, Emily.
Great. Thank you all so much for having me and for coming. It's been a really fun virtual visit day. As Andrew said, my name is Emily Cunningham, and I'm a Flatiron Research Fellow at the Center for Computational Astrophysics in the Flatiron Institute. And I'm going to tell you about how I like to use halo stars to test galaxy formation and evolution models and what we can learn from studying the Milky Way's stellar halo. So come on, we can do this. There we go. So what is the Milky Way stellar halo? So the Milky Way we know is a disky galaxy that's embedded in a huge halo of dark matter. And strewn throughout this dark matter, we see plenty of stars. We can see this image of the Latte galaxy from the Fire suite of Milky Way mass simulations, where we have our disk that's embedded in this halo of dark matter, which we can't see, but we can see that we have all of this very diffuse and yet also structured stellar component known as the stellar halo. And the way we think the Milky Way got its stellar halo is through the accretion of dwarf galaxies. So here I'm showing you the classic Bullock and Johnston simulations of Milky Way halo formation from accreted dwarf galaxies, where each one of these little colored blobs is a dwarf galaxy that's accreted onto a Milky Way-like parent potential. And we can see that we get these very beautiful streams and structures as these dwarf galaxies are tidally disrupted from the Milky Way's host potential. And so one thing you might notice from looking at these simulations is that you can see some of these very long extended stream-like structures are very long-lived, that they survive multiple passages around the galaxy. And that's because the dynamical times of these things are so long compared to the age of the galaxy that their kinematic properties retain a link to their initial conditions. Furthermore, the chemical properties of the stars in the stellar halo retain the link of the initial conditions in which they were born in their progenitor dwarf galaxy. So the goal of many halo surveys is to use both their kinematic properties and their chemical properties to learn about the dwarf galaxies in which these systems formed, and to learn about how the Milky Way assembled its mass from what kinds of dwarf galaxies and when. So of course, this is not just theoretical work. There's been plenty of evidence for this picture of hierarchical galaxy formation in the data. So here I'm showing you the very beautiful field of streams images from Anna Bonazza from the Sloan Digital Sky Survey, where SDSS really revealed a wealth of substructure in our halo, where we see the beautiful, particularly the Sagittarius stream, which is the most massive stream in the Milky Way halo, as well as smaller globular cluster streams. So this is really an opportunity to study hierarchical galaxy formation in progress by studying these systems. So why should we study the stellar halo? Why should you care about the stellar halo? There are a number of great reasons to care about the stellar halo. One, it contains some of the oldest, most metal-poor stars in the galaxy. So if you're interested in old metal-poor stars, the stellar halo is a great place to look. Furthermore, it's composed of the remnants of destroyed dwarf galaxies. So if you're interested in dwarf galaxies, in particular in the early universe, and studying dwarf galaxies that did not survive until present day, but were disrupted earlier in the age of the universe, then the stellar halo contains a really unique opportunity to study those systems on a star-by-star basis. In addition, we can use halo stars to trace the dark matter distribution of our galaxy and use them as dynamical tracers to study the mass distribution, in particular of the dark matter, which of course we can't see directly, and also the mass assembly history of the Milky Way, because we can see the remnants of many of these systems that have contributed to the buildup of the halo. We were very interested in reconstructing this mass assembly history, or this accretion history of the Milky Way, in order to properly place the Milky Way in a cosmological context. So to address many of these issues, what we need, as I stated previously, are kinematic information and chemical information. And the good news is that we already have a lot of it, and we're gonna get even more. So we're in the midst of what's been called a galactic renaissance, which I always think is a little fun. But why do people in my field say we're in a galactic renaissance? The good news is because we want to measure both 6D phase space and abundances of Milky Way halo stars out to the virial radius of the Milky Way. We can achieve this with very deep photometry, as we're getting from pan-stars. We, of course, have exquisite Gaia photometry, upcoming hypersonic PrimeCam, Rubin LSST, of course. We also need precision astrometry to achieve this goal, which we have, of course, achieved in great measure with Gaia. We'll continue to achieve with Rubin LSST and the Roman Space Telescope. And we need spectroscopy. So a number of Gaia, Gaia follow-up spectroscopic missions, Gaia itself, as well as upcoming spectroscopic surveys are really complementing the exquisite astrometric data set that Gaia has given us. So I just want to again emphasize how exciting it is to be someone in my field in the Gaia era, because Gaia has really transformed our image of the Milky Way. So this is a beautiful image of Gaia, of the Milky Way from Gaia, and it's truly transformed our understanding of our galaxy because it's given us so much information about particularly the tangential motions of stars in our galaxy. And so one of the big results from the Gaia era that I want to highlight is this emerging consensus in the field that the inner halo of the Milky Way is dominated by the debris from one relatively massive, relatively early merger that's known as the Gaia Sausage Enceladus. It has a lot of names. There are a number of discovery papers that have looked at this system in a few different ways, but I'll just stick to Gaia Sausage Enceladus to be agnostic, even though it is a mouthful. But you can see from this work from Rohan Naidu in the H3 survey, also of course co-advised by Anna Bonazza, that Gaia Sausage Enceladus is contributing up to 70% of the halo stars at 20 kiloparsecs in the galaxy. And so this was a really exciting finding that's come out of the first several Gaia data releases. But in addition to Gaia Enceladus, there are a whole bunch of other substructures in the Milky Way. So we have more information than ever about the kinematic structure of our galaxy. Where here I'm highlighting a few larger substructures that were characterized in work led by Rohan, and also narrower, more stream-like, very coherent, smaller, lower mass streams that have been studied extensively by Anna Bonazza. So we have more data than ever about the kinematic and chemical structure of our Milky Way. And the good news is that we also have a lot of really amazing theoretical models to work with too. So we've come, a long way from the Bullock and Johnston simulations, which are so awesome and still useful, but we have also these very interesting, exciting hydrodynamical cosmological zoom-in simulations. So here I'm showing you a movie from the Fire suite of simulations. This is the Latte suite of Milky Way mass galaxies. And we can see we have a lot of complications that are very important to galaxy formation, but are not included in Bullock and Johnston. So for example, we have a live forming disk. We have dwarf galaxies that are interacting with one another as they fall in. We have live dark matter halos. And so what I like to do is think about the simulations and observe the simulations to use them to think about what questions we should be asking of our data now that we live in this world where we have so much information about our galactic hemodynamical structure. How can we use the simulations to develop new questions and new ways of exploring those data sets? So in my talk today, there are going to be two parts. The first part, I'm going to focus on the dark matter distribution and disequilibrium in the Milky Way, and using halo stars as dynamical tracers to study our galaxy's mass distribution and signatures of disequilibrium. And then in the second part of my talk, I'm going to pivot and talk about the dwarf galaxy progenitors of the Milky Way stellar halo. So how we can use halo stars to learn about the dwarf galaxies that brought them into the Milky Way halo that have not survived to the present day. Okay. So in this picture of using Milky Way halo stars to trace the underlying dark matter distribution, I've eliminated one very critical component in the Milky Way that I want to bring up now, which is the presence of the Large Magellanic Cloud. So the LMC is the Milky Way's most massive satellite. It's located at a distance of about 50 kiloparsecs. And the classical picture of the LMC is that it was just sort of happily orbiting the Milky Way on about a 2 gigayear orbit on a pretty circular orbit and it had a total mass of on the order of 10 to the 10 solar masses. That's about 100th of the mass of the Milky Way. But in this classical picture, there was this very fundamental uncertainty on the tangential motion of the LMC. And so our picture of the LMC and its interaction with the Milky Way drastically changed when its proper motion was measured using Hubble Space Telescope data. So this was work led by Nitya Calabiolo. And what she found in her work is that the Large Magellanic Cloud is actually moving very near the escape speed of the Milky Way. And so this created what's now called the first infall picture of the Large Magellanic Cloud, where we think it is now interacting with the Milky Way for the first time. And so this really changed the paradigm for how we thought about the Large Magellanic Cloud's role in Milky Way dynamics. Furthermore, there's mounting evidence that the LMC is likely much more massive than we previously thought. So while the classical picture had the LMC being approximately 100th the mass of the Milky Way, we're now, the emerging consensus is that the LMC is closer to 10 to 20% of the mass of the Milky Way. So this is much more serious from a dynamical perspective. And I've just highlighted here on the left a number of the different studies that have made this argument that the LMC is quite a bit more massive than previously thought. And so this has extremely serious dynamical implications for the Milky Way. And this was recognized as early as 1967 in this great abstract from Abner and King that declares that the Magellanic Clouds on the Milky Way is indeed serious and that we need to worry about this. But this was even in the classical picture where it was on the order of 10% of the mass of the galaxy. So one person who's really looked at the Milky Way LMC interaction very closely is my colleague here at the CCA, whose name is Nico Garavito Camargo, where Nico has run very detailed, high resolution N-body simulations of just the Milky Way interacting with a Large Magellanic Cloud. And what Nico has characterized very carefully in his work is the fact that the Large Magellanic Cloud is inducing a wake in the dark matter halo of the Milky Way. So in this image, which is kind of funky, but is also very beautiful and captures what's going on, the LMC is this red point here, and the past orbital trajectory of the LMC is this red line. And the disk of the Milky Way is this little blue band in the center. And the contours here are indicating over and under densities. So this gray region trailing the LMC in its orbit, this is the classical Chandrasekhar dynamical friction wake, where as the LMC is falling in, particles are feeling attracted to the LMC and they form this overdensity trailing the LMC in its orbit, which in turn is exerting an effective drag force on the satellite. We also see this global response in the halo that manifests itself as this overdensity opposite to the LMC as it's coming in. Because of course, there are resonances all over the halo of the Milky Way with the LMC. And so another fun feature that's not exactly captured in this image, but that I want to mention is that at these masses, the Milky Way disk is actually dislodged from the center of its dark matter halo. And so it's actually accelerated towards the LMC, and the center of mass in the outer regions of the galaxy is not the same as the center of mass in the inner regions. And so all of these factors in tandem, this is all from just a simulation of a smooth Milky Way halo with one massive satellite, and just is demonstrating how serious and also interesting the effects are of this LMC Milky Way interaction. So the LMC is a huge source of disequilibrium in the Milky Way, but it's not the only one. So here I'm showing you a map. On the left-hand side, this is a map from Nico's simulations, which are again N-body simulations of Milky Way LMC interaction. And this is a map of the velocity anisotropy. And on the right-hand side, it's a map from one of the fire simulations that I made, where again, the velocity anisotropy corresponds to the colored point in each one of those grids. And we can see that in the LMC's case, we have these very large scale variations in the kinematic properties as a result of this interaction with the Magellanic Clouds. However, we also see variation in the fire simulation, even though, but we can see that this is correlated with smaller scale substructures, more like the typical accreted substructure that's creating differences in the kinematic properties over the positions in the sky. We see density differences and kinematic differences. So one question is, if we live in a Milky Way that isn't smooth like in NICO simulation, but actually has accreted all these other dwarf galaxies already and has this dark matter halo that's assembled over time through accretion and is expected to have these substructures here, how can we disentangle and pull out the signature, the predicted signature of the dark matter wake and the interaction with the LMC? So that was the question that motivated this paper that I worked on with Nico Garabito Camargo. The question we wanted to ask is if we could use spherical harmonics as a tool to disentangle perturbations to the Milky Way halo velocity field on different spatial scales. So here I'm showing you the spherical harmonics from L equals 0. L is the order, M is the degree of spherical harmonic. Whereas we go from L equals 0 down to L equals 4, you can see that we're resolving features on smaller and smaller spatial scales. So the idea is that perhaps using spherical harmonics, we can pull out the signal from the LMC and disentangle it from signatures due to galactic substructure that's independent of the LMC. So to show you how this works, first here I'm showing you velocity maps of a spherical shell from Nico's simulations, again, just smooth Milky Way, LMC interacting. And so this is a spherical shell centered on 45 kiloparsecs, where each pixel contains the mean velocity for that position in the sky. So the position of the LMC here is shown by the star. And then I have radial velocity on the far left, polar velocity in the middle, so up and then up and down in the spherical sense, and then rotational velocity on the far right. And first of all, you can just see the perturbation. You can see that there are fluctuations in the pure equilibrium model, which essentially, you know, the vast majority of estimates of the Milky Way mass in the past have assumed a perfectly equilibrium model. Each one of these maps would be completely smooth with no features. But we see that just the LMC alone is inducing these features in these maps. And so the lower panels are showing you a relatively low order, so L max equals 5, expansion of these different velocity maps. And what you can see is that the low order expansion is recovering the salient features of these maps fairly well, because these are large scale perturbations that are being induced by the Large Magellanic Cloud. And I want to highlight some of that here. So in this radial velocity map, for example, the star is the position of the LMC. It's colored yellow here because it's moving outward. It's just come through pericenter and is moving outward away from the galaxy. And so you can see that trailing the LMC in its orbit, which really basically goes like this in angular space. You can see that you have these stars that are moving the same direction as the LMC, trailing it in its orbit. And these are stars that are trapped in that traditional Chandrasekhar wake. In addition, on the whole opposite side of the halo, you see there's also this net outward motion, and that's a result of this, they call it the collective response, which is the global response of the halo to the perturbation. Similarly, if we look over here at the V5 maps, right near the position of the LMC, you have these converging motions. And these are, again, stars that are being accelerated towards the LMC's orbital path that are getting trapped in the wake that's trailing the LMC in its orbit. And so one thing we can do once we've done the spherical harmonic expansion is quantify these features. So here I'm showing you on the left velocity maps from these simulations of just radial velocity here for 3 different distances out into the halo. And so we have 45 kiloparsecs on top, 70 kiloparsecs in the middle, and 100 kiloparsecs in the bottom panel. And what we can see is just even visually, these are shown with the same color bar. You can see that the distortions are getting more intense and more different as we go out and out to farther and farther radii. And we can quantify this with the power spectrum. So L equals 1 is the dipole. And we can see as we go out to farther and farther distances, for purple is 45, 70 is in orange, blue is 100 kiloparsecs. The power in this dipole mode is increasing as a function of distance. And this is due to the modal response, the global response, but it's also due to the fact that the Milky Way disk has been dislodged from the center of its dark matter halo. And that results in a net motion that is increasing as you look farther out into the halo. And so we measured this, we quantified this again in a paper that was led by Nico, where he did a full expansion of the potentials and the density distributions in these simulations. But what we found is that this dipole, the magnitude of this dipole is increasing as a function of distance. And it's of course more dramatic for more massive LMCs, but that also the center of mass is like the distance from the center of mass to the center of the Milky Way disk is changing as well as a function of distance out into the halo. So that's an aside, but that's some updated work that Nico led more recently in this paper. But back to the paper that we worked on in 2020, we also looked at the mass dependence because there are 4 different mass LMCs that were run as a part of this suite of simulations. And we can compute the power spectrum for different LMC masses. And what we found is that the shapes of the power spectra are actually pretty similar for each one of the LMC interactions, but their magnitudes scale very clearly with the mass of the LMC. So this is, again, useful for wanting to quantify the effect of the Milky Way halo. If we could measure something like this in the Milky Way halo, then we could potentially have additional constraining information on the mass of the LMC. But I motivated this by discussing the fact that it's complicated to observe these signatures if you're in a cosmological halo that's been built up through accretion events. And so in order to test if we could use spherical harmonics to disentangle signatures due to smaller scale substructure versus large scale perturbations like the Magellanic Cloud, we looked to the Bullock and Johnston simulations. And what's significant to note about the Bullock and Johnston simulations here is that there is no live dark matter halo in these simulations. It's just a time evolving analytical potential. And there's also no dwarf interactions. So there's no live dark matter wakes in these simulations. So we're completely ignoring that in these maps, in these simulations, which is good because this lets us pull out that signature from the LMC. So when we looked at the Bullock and Johnston simulations, we looked at these, I call them like the extreme accretion histories, where you can put together a halo from Bullock and Johnston that's only comprised of high luminosity satellites or only comprised of low luminosity satellites. So those are the 2 maps that you see here on the far left. Similarly, you can create a halo that is only comprised of super recent accretion events and only comprised of really early accretion events. So these are the 2 maps here in the center. And you can immediately see by eye that you do get fairly large scale features in this high LSAT map and this halo that's comprised of recent accretion events. And this is revealed as well in the power spectrum when you compute the power spectrum. So here is the power as a function of order, the power spectrum. The LMC power spectra for radial velocity are shown by the gray band, where the gray band is encompassing the different masses of LMCs that we ran, or that Nico ran. And the halo that's comprised of high luminosity satellites is shown by this gray line, and the recently accreted halo is shown by this pink line. And you can see that for all these maps at larger order, so on smaller spatial scales, there's quite a bit more power than in the LMC, which is to be expected because we know there are smaller scale perturbations in these halos. But that the recently accreted halo and the halo made of very massive satellites can contribute significant power to the power spectrum at low orders, even like L equals 1, L equals 2. So this is a concern if we want to identify this signal from the LMC. However, we do have a bit of luck in our favor, which is that we believe the Milky Way has had a relatively quiescent recent accretion history, with 2 very major exceptions worth noting. One is the Large Magellanic Cloud, which is of course in the process of disturbing the Milky Way. And the other is the Sagittarius stream. So here I'm just showing you a beautiful map of the Sagittarius stream from the Pan-STARRS survey from Bronimer Cesar's 2017 paper. And you can see that this stream has debris all over the sky, extending out to over 100 kiloparsecs that we know of so far. It is the most massive stream in the Milky Way, and it's sort of notorious for confusing Milky Way halo studies. So what we wanted to do in this paper is say, we've seen that if we're going to worry about substructure obscuring the signal from the LMC, excuse me, from the spherical harmonic signal, we need to worry about recent massive accretion events. So we should try to incorporate a Sagittarius into our calculations. Excuse me. So to do this, we took some Sagittarius models. We used 2 Sagittarius models to do this. One that I'm showing here was given to us from Dennis Urkel, and the other one is the publicly available Dirichlet-Loeb model. And what we did is we made some simple assumptions, assuming that Sagittarius, the total mass of Sagittarius is approximately, 10% of the total halo mass, and injected it onto the stellar halos from the N-body simulation. So this is, a rough calculation and has a lot of simplifications, but it could give us a starting point to explore how we think Sagittarius might contribute to this signal. So here's, again, radial velocity on the left, polar velocity on the middle, and azimuthal velocity on the right. And then the lower panels, I'm showing the power spectrum. So the combined Sagittarius and LMC power spectrum is shown by the purple line, and then the thick line. The LMC only is shown by the dashed line. So these are, for the purple is 45 kiloparsecs. I'm sorry, it doesn't say this here. These are shells at 45 kiloparsecs. And then the difference between the two is the dot dash line. And so I've only shown you here the full power spectrum for including Sagittarius at 45 kiloparsecs, because if you look at larger distances, the differences are very minimal, and there's significant power from the LMC only at these large distances. So we don't even really need to worry about it at large distances, was what we found. But we can see at 45 kiloparsecs, there is a significant contribution from Sagittarius contributing to the power spectrum. But my takeaway from this is that, yes, it is contributing, but this is in the regime where we have included all Sagittarius stars. We haven't made done any substructure removal or removed any stars that we know belong to Sagittarius. And Sagittarius is pretty well mapped, at least in the inner regions of our galaxy. So we have every reason to believe that if we make some reasonable models if we model contamination from Sagittarius in a relatively straightforward way, that this should not overwhelm the signal that we're expecting from the LMC. So to summarize part 1, the LMC-induced dark matter wake is affecting the global properties of the Milky Way stellar halo, and spherical harmonics could be a useful tool in terms of characterizing and quantifying the kinematic patterns that are induced as a result of the interaction of the dark matter wake and the LMC. We found that debris from recent massive accretion event can cause large power in the angular power spectrum over many scales, but including low, relatively, large spatial scales, which means low order spherical harmonics. But that, when we did do some analysis using models of Sagittarius, and found that while we feel it should be modeled, if you're going to make this calculation, it should not overwhelm the signatures from the LMC-induced dark matter wake. Meanwhile, I just also, of course, have to address some very exciting observational results that came out since I came out with this paper in 2020. One of these is a great paper that came out in Nature, led by Charlie Conroy, analyzing the density field in the Milky Way halo, where they found an overdensity trailing the LMC in its orbit, as well as an overdensity on the opposite side of the galaxy, which is consistent with the predictions from MECO simulations. Excuse me. So this is very exciting. In addition to analysis of the density field, there was also an analysis of the velocity field. And this is work led by Mike Peterson and Jorge Penarrubia, but also Dennis Urkel did some work analyzing the line of sight velocities. But what they did in this paper was model the velocity, the reflex motion, so the motion of the disk with respect to its outer halo, since the disk is being displaced by the LMC from the center of its dark matter halo, modeled this effect as a velocity dipole. And so the direction of the dipole is what's indicated by these contours, where each color is a different sample that they used to make this measurement. And so they found a net velocity dipole that's pointing in the direction of where the LMC used to be in its orbit. So I think these results are super exciting. We're learning more and more about how complicated our galaxy is in both the simulations and the data. But my one note of caution, and one thing I think we need to keep looking into, is what these effects look like in cosmological halos, given that the majority of this work on the dark matter wakes has taken place in idealized n-body simulations with, say, one satellite and the host. So I want to advertise some work that's being led by Alex Riley, who is a finishing grad student at Texas A&M. He's almost a postdoc, who joined us for the CCA Big Apple Dynamic Summer School and did a great job working on this project with me, and also Adrian Price-Whelan and Nico and Catherine Johnston and Robin Sanderson, where we have been looking at velocity dipoles in the fire simulations. So looking at examples, as you see here, where we have an analog between the Milky Way LMC, as well as simulations where there's not an interaction with a massive satellite, and using the same technique that they use in the observations to model the velocity field as having a dipole, and see if we can necessarily link those dipoles to interactions with massive satellites. And so just a preliminary result from Alex here, where he's showing you the motion of the LMC analog across the sky over time. So this is the LMC's orbit, and time here is 0 at pericenter, the first pericentric passage of the LMC analog. And so this is before pericenter and after pericenter. And what he did was measure a velocity dipole in this simulation as a function of time. And he found that this dipole, just like in Mike Peterson's paper, is pointing in the direction of where the LMC used to be in its orbit, which makes sense because it's spending more time out there and it's whipping around at pericenter quite quickly. So there's more of a response at large distances in the halo where the LMC is spending more time, and in the direction where it came from as opposed to where it's going. So this is a really cool result that we're finding that's consistent with what was found in the observations, but he is also finding that substructure remains to be an issue, that if there are coherent structures that you don't know about, that you can't subtract off beforehand, this could give rise to a false detection of a velocity dipole. So stay tuned for more results from Alex. And then finally, I just want to mention that this problem, I think, is really exciting for Rubin-Roman synergies. So I think in particular, combining Rubin, which will have amazing wide field coverage of tangential motions in conjunction with Roman, which can do very targeted, specific proper motions, very precise proper motions, is going to be perfect for this problem, given that if we look at the tangential signatures that are predicted to come from this interaction, we have both large scale features and small scale features. And so I think this is very exciting for Rubin-Roman synergies. So just to summarize again, part 1, we can use spherical harmonics to disentangle kinematic patterns and quantify kinematic patterns in the halo velocity field, and disentangle sources of disequilibrium on different spatial scales. We think Sagittarius could be an issue, but if it's modeled, it should not overwhelm the signatures from the LMC-induced dark matter wake. Though I will mention the caveat that because we just injected a Sagittarius model on top of the LMC, we did not consider dark matter particles that might have been stripped from from Sagittarius, or interactions between the LMC and Sagittarius. So I think that's an exciting future direction as well. And looking forward, I also think we need to spend some time looking for wakes in cosmological simulations, quantifying them in cosmological simulations where we have more realistic halos that have been assembled in a cosmological context. So that's also ongoing work that Nico and I are thinking about here at CCA. Okay, so that was part 1. For the second part of my talk, I'm going to switch gears and talk about the dwarf galaxy progenitors of the Milky Way stellar halo, and think about how we can use observations of halo stars to learn about the dwarf galaxies that have contributed to the buildup of the stellar halo. So to motivate this talk, I'm going to start with these 2 figures here. And this figure is the way I say it's like looking at the formation histories of these two Latte galaxies. And what I mean by that is that I'm showing you here, it's really the star formation histories of these galaxies. So these figures, each one is a 2D histogram of the formation time. So 0 is early universe, 13.7 is present day, versus formation distance. So that's how far away a star particle is from the main host galaxy in the simulation over time. So if you sort of orient you in this plane, I'll highlight a few features. First, we have these very thick bands at the bottom in each of these panels. And these are stars that are forming in the disk of the host galaxy. They're forming at low formation distance, which means near the center of the host, which means disk, basically. Then all of these streaks and wiggles that are at larger formation distances are stars that are forming in dwarf galaxies. So for example, in M12M, we have this wiggle here, where this is a dwarf that has had a pericentric passage with the main host, but it's still forming stars and is out at 200 kiloparsecs at redshift 0. And we have many dwarfs at larger distances that are more isolated from the main host. But we also have accretion events, and we have all of these stars that are contributing to the stellar halo. So for example, M12R has an accretion history that is characterized by very recent massive accretion. And we can see that in this plane by these very thick bands that are then interacting and hitting the disk at late times in the simulation. And so the fact that they're very thick and bright in this plane means that there's a lot of star formations. These are very massive things that are interacting with the Milky Way host, Milky Way-like host near the end of the simulation. Whereas in M12M, we have a lot of activity here at early times, but no major late time huge interactions with the disk like we see in M12R. And so there are a number of different ways in which you expect galaxies with different formation histories to be different. But one way that we can see that these galaxies have had different formation histories is through their chemical abundance ratio distributions. So that's a mouthful. And so I'm going to use the phrase cards. But when I say card, all I really mean, this is for the purposes of today, this is more than enough, is to think about the distribution of stars and the magnesium over iron versus iron on hydrogen plane. So if I say card, I mean abundance distribution, predominantly comparing these elements, magnesium over iron versus iron on hydrogen. And so we can immediately see that if we look at the abundance distributions for these different Latte halos, that they visibly look very different. So for example, M12R is characterized by this very late time recent accretion from these very massive dwarfs. And if we look at the abundance distribution of its halo, it's extending out to very high relatively high metallicity, and the distribution is turning over in magnesium on iron because these are very extended star formation histories that have been enriched by type 2 supernovae and in type 1a supernovae, and have this characteristic turnover as the dwarf continues to evolve over an extended period of time. In contrast, we have M12M, which is characterized by early accretion as opposed to the later time accretion. And if we compare these two distributions, we can see that M12M has a higher relative alpha abundance compared to M12R and is in general lower metallicity. So we can see with our eyeballs that these are very different distributions. The goal of this paper was to ask the question of how we can go from observing an abundance distribution and then making quantitative inferences about how this galaxy came to be. And so the two questions I want to focus on today are, how can we go from this abundance distribution to making quantitative inferences about the mass spectrum of accreted dwarfs? So what fraction of the mass of the halo came from dwarf galaxies of what mass? And then also the mass accreted as a function of time. So when did the Milky Way consume what fraction of its mass, for example? And so the idea behind this paper is to use what we call card templates. What this is it's an empirical approach, where the idea is that if we have a bunch of templates for dwarf galaxies that have different stellar masses and different quenching times, maybe we can back out how much of the Milky Way, maybe we can back out the properties of the dwarf galaxies that contributed to the buildup of the Milky Way. So there's a lot going on in this figure. So let's hide some of it for now. Oh, I also want to acknowledge that this was a great idea from Dwayne Lee and Catherine Johnston in a paper in 2015 where they tested this in the Bullock and Johnston simulations, but those required prescriptions for chemical abundances. They were not self-consistent. So this is a chance to test this technique in a more realistic setting. But in this grid of templates, as we go from the top of the grid to the bottom of the grid, we're increasing in stellar mass. So the top row here is for dwarfs with stellar mass of 10 to the 6 to 10 to the 6.5. And the lower column is 10 to the 8.5 to 10 to the 9 in stellar mass. And then we increase in quenching time from left to right. So if we look in the top left corner, this is what the abundance distribution looks like in fire for a relatively low mass, so stellar 10 to the 6, galaxy that quenches very early in the simulation. So within the first 2 gigayears of the simulation. So we can see it's very metal poor, it has relatively high density at higher alphas, which is what we would expect. In contrast, this distribution is for a very massive satellite of the Milky Way that is disrupted and quenches very late in the simulation. So within the last 2 gigayears of the simulation, we can see that its abundance distribution extends to higher metallicity and to lower alpha. So the idea here is that if we have this grid of empirical templates, we can solve for the coefficients of modeling our full abundance distribution as a linear combination of each template. And in principle, what that would mean is that the coefficient with each template corresponds to the fraction of mass in the Milky Way halo that came from accretion events of this stellar mass and quenching time. So if we have our empirical templates, we can just solve for the coefficients that correspond to each template and then infer the mass spectrum of accreted dwarfs and how much the quenching time distribution for the accreted dwarfs. So to create these templates, I relied on the Halo Progenitor catalog from Nand Panitambazal, who is an outstanding graduate student at University of Pennsylvania, working with Robin Sanderson, where he wrote a really fun paper on the properties of stellar streams, but also satellite galaxies and phase mixed debris in the fire simulations. But also excitingly, I wanted to plug that Nand's catalog is publicly available. So if you are interested in streams, in cosmological simulations, please go check out his work and check out his database that's available. It's hosted at Flatiron via FlatHub, and you can play around with the different properties of the streams, and it's very fun, so go check that out. Also at this point, I wanted to make a disclaimer, because I know there are a lot of people on this call who probably spent a lot of time looking at these abundance distributions in the data. And you might be noticing that the abundance distributions from fire look a little strange. And I wanted to make the disclaimer that yes, you're absolutely right. And I know that this is true, that there are a few reasons why the Latte distributions, abundance distributions don't match the observational data, and that this project is not designed to create templates for use in observational data. So we know, and this was first pointed out in a great paper from Ivana Escala, that the fire dwarfs are too metal poor compared to the observed dwarfs. And so there are a number of reasons why this might be true. One that was recently explored in a recent paper from graduate student Pratik Gandhi working with Andrew Wetzel is the delay time distribution for type 1a supernovae, and implementing a more modern model for that, including metallicity dependence, has really improved the mass metallicity relation discrepancy with observations. Another reason is that particles are initialized with a metallicity floor. And so what that means is there's a maximum alpha abundance for a fixed iron abundance. And so that's what gives rise to these ridges in the simulated distributions that we don't see in the data. But this is changed in Fire 3. So stay tuned for how these look in Fire 3, because they're making a lot of improvements on these efforts in the simulation side. But the disclaimer is that these templates are not intended for use with the data. The point is to think about if we had an empirical template set that works in a self-consistent cosmological simulation, could this technique then work with a set of empirical templates derived from observational data in the real Milky Way halo? So the question we wanted to ask is just this idea of using an empirical template set for distributions. Does it work at all in a hydrodynamical cosmological simulation where we have diverse formation histories, diverse star formation histories, all kinds of complications that were not included in the initial Bullock and Johnston simulations? But also, you know, if the question is that if you have the stellar mass and the time a halo progenitor took to form that stellar mass, can you predict its abundance distribution using empirical templates? So that's sort of turning this question on its head. So if I know how long a dwarf galaxy took to form its mass and what its mass is, can I just sort of read off essentially what its abundance distribution should look like? So the first question is, does this really work? And the answer is sometimes yes, and sometimes yes, surprisingly well. So this is our example success story, which is from the Halo M12F from the Latte suite, where we find that if we create an empirical template set from dwarf galaxies in the Fire suite, we can create a very good model for what the abundance distribution looks like in the halo. So here is the M12F stellar halo simulation abundance distribution. And in the middle is the model abundance distribution that I created from combining my different templates. And what I found is that I'm able to get a model with very low residuals. So just to clarify here, the stellar halo are phase mixed debris and streams in this simulation. And the model is created from templates of just satellites, so just dwarf galaxies. And we find that we get a very good model. And promisingly, if we want to infer properties of the assembly history, so here is the mass spectrum of accreted dwarfs. So this is mass of accreted dwarfs as a function of what fraction of mass it contributed to the total stellar halo. The truths are in gray, and 3 different template sets that I created, tweaking what I was contributing to what template set. You can see that all template sets return excellent agreement with the true mass spectrum of accreted dwarfs, where the residuals for this model are shown in the bottom panel. Similarly, I can look for mass accreted as a function of quenching time. And while the agreement is not as strong as it is with the mass fraction, given that this was just an empirical approach with a linear model, that really this model knows nothing about physics, it only has its abundance distribution and the templates, I thought that it did pretty well. But yeah, it's not quite as good for quenching time, but but still pretty good given all these considerations. And the good news is that M12M is not totally unique. It might be our best case scenario, but that we do recover the mass spectrum of accreted dwarfs to within 10% using our dwarf galaxy templates for 5 out of the 7 Latte halos, which is 4 out of the 7 Latte halos, which is pretty exciting. It was better than I thought it was going to do. But we also have to be honest about our failures, and there was a failure story as well. So this is the Halo M12C, where the simulation, the stellar halo from the simulation is shown here on the left again, and the model is in the middle panel. And when we look at the model residuals, we immediately see that it's not doing a good job of representing the underlying data. And we can see that there's this bright feature here at metallicity of about -1 and alpha of about 0.25 that is not represented in the template set, and so then is not well recovered when we're trying to model this abundance distribution. And so unsurprisingly, given that we have a poor fit to the data, our inferences of the assembly history are not very good, where really what's happened here is that this dwarf, this halo progenitor, for whatever reason, I can get to that later, but it doesn't enrich to as high metallicity as you would expect given its stellar mass. It has this buildup of stars right here. And what this is ultimately due to is a starburst that's triggered by its first pericentric passage. So it actually has this huge burst of star formation at late times, which is not seen in the template sets that are created from satellite galaxies. So this is a failure, but it's also indicative that something interesting was going on with this halo progenitor. And the good news is that the first clue that we will inaccurately infer the accretion history is the fact that we get a poor fit to the data with our model. So for M12C, we have very high model residuals. So here, the residuals that I'm showing you on the color bar are the residuals that are plotted on the x-axis in both of these panels. And then in the top panel, the residuals on the y-axis are reflecting how accurately we inferred the mass spectrum. And the lower panel are the residuals demonstrating how accurately we inferred the mass as a function of quenching time. And so M12C has very high model residuals in both its fit to the data and the inferred assembly history properties, whereas M12F has much lower model residuals in both the actual model of the data and the inferred assembly history properties. So to summarize part 2, the chemical abundance ratio distribution, or CARD, of the stellar halo is rich with information about the formation history of the galaxy, and that modeling the CARD of the halo as a linear combination of contributions from dwarf galaxies of different masses and quenching times is sometimes effective at recovering the assembly history of the galaxy. Not in all cases, but the good news is that when our method was failing, we had signals in the form of forfeits to the data, and we were learning that something very interesting was going on with that halo progenitor. And so I just wanted to close by mentioning that it's such an exciting time to be thinking about chemical abundances, both in the Milky Way halo, in dwarf galaxy halos, in Andromeda's halo. Of course, Yvonne is here and has done a ton of work on resolving, on measuring abundances in Milky Way, in M31's stellar halo features, and of course also M31 satellites. And so it's a really exciting time to be thinking about what we can do with all of this information that we're getting for chemical abundances of individual stars. And, where we were ways from, making all of these abundances exactly consistent and analyzing them in a consistent way, but it's still so exciting that there's so much data coming out, and there's only going to be more with, SDSS-5, Subaru PFS. There are all these programs, so that we're really learning more than ever about the chemical and chemodynamical structure of our galaxy. So I will leave my conclusions up and take questions. Thanks.
Great, thank you, Emily. We have plenty of time for questions. I'm guessing there are going to be several, so you just raise your hand in the Zoom chat. So Ivana, you have a question?
Yeah, great talk, Emily. I was just wondering, in terms of the LMC weights, you talked about Charlie Conroy's paper, which I'm assuming was based on H3, I actually don't know, but then and Roman and Rubin. So I was wondering, I guess, about the near term in between time in terms of like what observational advances we might expect, if any, in terms of probing the velocity distribution of the outer halo and looking at, perturbations that you may expect based on things like the LMC.
Yeah, great question. So in terms, you're right that I kind of skipped a major intermediate step, which I think is much more imminent, which says radial velocities in the outer halo. And so that's something that I'm super excited about and interested in, because these signals from the wake are the signals from the signal that is due to the displacement of the disk in the halo gets stronger as a function of distance until it eventually levels off. And I think we know essentially nothing about the galaxy outside of 100 kiloparsecs. They're only on the order of 10 stars that have published radial velocities at those distances. And so I think in the coming years, there will be significant spectroscopic efforts focusing on distant stars. I know there will be within SDSS and within DESI. And so that will really be extremely useful for looking for radial velocity differences in the north and the south, for example, and also just in general, getting a better handle on what's going on in the outer halo, because it's still such a mystery in so many ways. So I think, Roman will be amazing for the tangential components of the signatures, but you're totally right. There's an intermediate step, which is getting RVs of distant stars in the halo. Yeah.
Great, thanks.
We have a question from Anna.
Yes. Hi, Emily. Thanks for the great talk. Had actually the questions if there's time, so I'll start with that one on the first part. It seemed like when you were doing the decomposition of the different mergers in the spherical harmonics, that there was more power in the odd L's. And there felt like there was sort of a zigzag pattern. And so I'm wondering if kind of first how significant this is, and if and assuming that it is, can it be used to sort of keep the number of free parameters down if you were to try to constrain these parameters directly from the observations?
Yeah, absolutely. So that's a great point. And we actually did a whole appendix on this in the paper because it was very confusing to me, but I am very fortunate to be a colleague of Rodrigo Luger here at CCA, who actually does spherical harmonics for modeling surfaces of stars. But where he showed me is that if you have banding, I might get this flipped, but if you have some kind of band, which you could think of as like a stream that's all moving on constant, relatively constant velocity, that's a fairly circular stream, then you get spikes in odd modes. And if you have something where you have big spots, so you have, for example, like a very radial stream that's coming in one direction and then about 180 degrees opposite going out the other direction, then you get the spikes in the odd modes. So what I take from that is that spherical harmonics is honestly maybe not the best basis for the streams. It does really well for the wake, like it's really getting the wake, but for the streams, maybe we want to be thinking of a slightly different basis. But yeah, those features, streams, it turns out that the halo substructures tend to create these kind of funky streams. So I think you're right, like that we should pick a basis that works a little bit better for the substructures. But it was not a bad place to start. Yeah.
No, for sure. I mean, definitely informative, right? Like even if you just decide to keep some low L, like number of L components for the wake and then add the streams as some different parameterization. That's super interesting. Okay, I don't see other hands, so I'll go ask my second question, which is on the cards modeling. So I was wondering if this would be like an application of a machine learning, where a machine learning would make sense, like a neural net, where you could, and if that could capture some of that, because it seems like with the templates, you check that just kind of select like the existing dwarf galaxies, but are not sensitive to the like response that they induce when they come into when they merge in the host halo. Whereas I feel like if you're maybe doing some sort of training a neural net, like maybe some of that could be captured. So I was wondering if, your thoughts in this general topic.
I hadn't thought about that, but I actually love that idea, because you're right that if there is star formation, for example, triggered by the interaction with the host, that is certainly not represented in the isolated dwarfs. One thing I had thought about is maybe doing some kind of template set where I tune doing what we were discussing earlier with there's new functionality for Fire that lets you implement different yields in post-processing. And so what this will let you do is match your simulated templates. You can tune your simulated templates to match your observations. And then you could kind of use the simulations to fill out the different gaps that you don't have in the observations. And I could see somehow maybe like some kind of machine learning application fitting in there as well to think about, interaction. Yeah, I had that. I'm sorry, my gears are turning, because I think that's a great point about teaching the templates that something might happen after infall and how we could go about that. Yeah, that's a great point. Thanks.
Thanks again for the talk. I really enjoyed it a lot.
Thanks.
I guess I have one question that was kind of inspired by your answer to Anna's first question. So in the spherical harmonic analysis, you've looked at the amplitude of those harmonics. Have you also thought about looking at correlations between the phases of any of them? Would that be interesting information there?
Yeah, I don't think I looked at that explicitly, but I think that's a great point. And that could be a great point for, again, disentangling. So I focused kind of just on the power spectrum, but of course there's much more information once you're working with the phases. And so I think that's a really good point. And it's something that would be worth thinking about, especially when you're thinking about, for example, comparing signal with Sagittarius versus not. I think we may have looked at that in the paper, and the phases were distinct, and that was reassuring now that I'm remembering. But we didn't do like a detailed analysis of the correlations of the phases or anything like that, but that would be very useful, I think.
That's good. Any last questions? If not, then let's thank Emily again, and thanks everyone else for joining us today.
Thank you all for coming.
Thanks, Emily.
Yeah,
thanks, Emily.
Interesting.
Thanks.
Thanks.